Have you ever stopped and wondered what the world is really made of? I mean, deep down. For centuries, that's the exact question scientists have been obsessed with. It's been like a massive detective story, trying to get a picture of the atom, the fundamental building block of literally everything. And that journey, well, it's taken us from a simple, solid ball to a strange and beautiful cloud of pure probability. So let's follow the clues and see where this mystery takes us. All right, so here's our game plan. First, we'll meet the main players, the atom's core components. Then, we'll jump in a time machine and see the first sketches scientists made of this invisible thing. After that, we'll see how a guy named Niels Bohr came in and saved the atom from total collapse, which then leads us to the modern fuzzy picture, the electron cloud and its surprisingly specific address code.
Okay, first things first. Before we can even begin to talk about what an atom looks like, we've got to meet the cast of characters. What is it actually made of? So, the textbook definition you probably learned in school is that the atom is the smallest possible piece of an element. But here's the twist. It turns out this smallest part is actually made of even smaller parts. And that discovery? It changed absolutely everything.
Now, check this out. It might look a little like a secret code, but it's really the atom's ID card. It tells you everything you need to know about its core. That Z on the bottom, that's the atomic number. It's just a count of the protons, and it's what makes an element, well, that element. The A up top is the mass number. That's the total number of protons plus neutrons. It's a super neat way to pack in all the vital stats.
So, what's the big takeaway from this chart? Just look at the masses. Protons and neutrons are the heavyweights, right? They both have a mass of about 1. Now look at the electron. Whoa, it's almost 2,000 times lighter. It's basically nothing. This tells us something huge. Pretty much all the mass of an atom is crammed into its tiny, tiny center.
Okay, so we've met our three players, the heavy proton and neutron hanging out in the middle, and the super light electron zipping around the outside. But knowing the ingredients is one thing. How are they all arranged? That one question kicked off this epic quest to draw a picture of something nobody could ever see. Let's take a look at their early drafts. This whole thing didn't happen in one big aha moment. Not at all. It was more like a series of rapid-fire software updates. Each new model came along and fixed a major bug in the last one. And in just over a century, we went from thinking of it as a boring little ball to this wild, fuzzy cloud.
So right after the electron was discovered, a scientist named J.J. Thomson came up with this idea. He called it the plum pudding model, but let's be honest, it's a blueberry muffin. Just picture it. You've got this ball of positively charged cake, and then dotted all through it are these little negative electrons, the blueberries. Simple, right? A pretty logical first step.
Yeah, the muffin model was cute, but it had some pretty big problems. For one, it couldn't explain why the positive cake and the negative blueberries didn't just all mush together. But its biggest flaw was assuming that positive charge was just spread out all evenly, an idea that was about to get completely blown to pieces.
And this is the experiment that changed the game. A guy named Ernest Rutherford decided to test the muffin model. His plan was simple. Fire tiny positive particles, think of them as microscopic cannonballs, at a sheet of gold foil that was unbelievably thin. If the atom was really like a soft muffin, all those little cannonballs should just zip right through. And most of them did. They went straight through. But then, something absolutely crazy happened. A tiny, tiny fraction, like 1 in 20,000, bounced right back. Rutherford himself said it was as ridiculous as firing a 15-inch naval shell at a piece of tissue paper and having it come back and hit you. It could only mean one thing. The positive charge wasn't a soft pudding. It was a tiny, hard, dense core at the center, the nucleus. The atom was mostly empty space.
So we traded the muffin for a mini solar system, a tiny nucleus with electrons orbiting it like planets. Awesome, right? Well, no, there was a huge fatal flaw. According to all the physics they knew at the time, an orbiting electron should be giving off energy constantly. It would lose speed and spiral down into the nucleus in a fraction of a second. If that were true, nothing should exist. The model was completely unstable. So, the atom was on the brink of self-destruction, and physics needed a hero. That's when Niels Bohr, a brilliant Danish physicist, stepped onto the scene with a solution that was as bold as it was, well, weird. Bohr basically said, you know what? Maybe the old rules of physics just don't apply when you're this small. He proposed that electrons couldn't just be anywhere they wanted. No, they were locked into specific, fixed orbits. He called them energy levels. kind of like train tracks around the nucleus.
And here's his most radical rule. He just declared it. He said as long as an electron is on one of these special tracks, it just doesn't lose energy. It doesn't spiral to its doom. It's just stable. It completely broke with classical physics, but it was the only thing that explained why atoms don't just, collapse.
And this shows how it all works so beautifully. An electron can jump to a higher track if it absorbs a very specific packet of energy. And then, when it falls back down to a lower track, it spits that energy back out, usually as a little flash of light. This perfectly explained why different elements glow with specific colors when you heat them up. It's the light from their electrons jumping between these fixed levels. So Bohr's model was a massive success. It perfectly predicted everything about the hydrogen atom. But that was the problem. It only really worked for hydrogen. As soon as you tried to use it on more complicated atoms, the math just fell apart. It was a monumental step forward, for sure, but it wasn't the end of the story. Things were about to get a whole lot stranger.
Okay, this is probably the biggest mental shift in this entire story. Bohr's model had electrons on neat, predictable paths, which he called orbits. You knew where it was and where it was going. The new quantum model, it throws all of that certainty right out the window. It gives us something called an orbital, a 3D region of space where you just have a probability of finding the electron.
So what kicked all this new weirdness off? It started with a guy named de Broglie, who asked a seemingly simple question. He said, look, we know light can act like a wave and a particle. So why can't a particle, like an electron, also act like a wave? And the crazy part is, he was right. An electron isn't just a tiny spinning ball. It has a wave-like nature that's sort of smeared out in space. And that wavy nature leads directly to one of the most famous ideas in all of science, Heisenberg's uncertainty principle. What it says is that there is a fundamental limit to what we can know. The more precisely you nail down an electron's position, the less you can possibly know about its momentum, where it's headed. And this isn't because our tools aren't good enough. It's a basic rule of the universe. A neat, predictable orbit is literally impossible.
So, if we can't know exactly where an electron is, are we just totally lost? Nope. This is where physicists got really clever. They came up with a system of 4 quantum numbers that work together like an address for every single electron in an atom.
And it's really just like a mailing address. The first number, N, tells you the main energy level. Think of that as the state. The next number, L, tells you the shape of the orbital. That's the city. The third number, M, tells you how that shape is oriented in space. That's the street address. And finally, the spin, S, is like the apartment number. And there are only 2 choices, which we just call up or down.
And here's the absolute coolest part. When you do the math using those quantum numbers, what pops out are these incredible, beautiful, complex shapes. These aren't paths the electron follows. They're 3D probability maps. They're fuzzy clouds that show where the electron is most likely to be at any given moment. This is the true face of the atom, not a little solar system, but these amazing, intricate clouds of possibility.
And that leaves us with one last, truly mind-bending thought. If the atoms that make up you and me and the chair you might be sitting on are 99.999% empty space, and the only stuff in them are these fuzzy clouds of pure probability, then what does it even mean for something to be solid at all? The world is so much stranger and more beautiful than it looks.